Now that we've helped people customize and
Okay, so sorry about the late start. I had to restart the stream in my and the thing that I used the program I used to stream. I had to restart it a couple times for some reason. YouTube kept saying it wasn't getting any data, even though it looked all right. But anyway, so welcome back. We're almost at the ending point, so we will have almost kind of exhaustively gone over all of the points I wanted to touch on for all of this non-Euclidean stuff. So the thing that I wanted to discuss today was non-Euclidean distance. But before I say anything, I'd gotten a couple of more emails about, I know you all have questions about the homework 6. So I extended the homework 6 essentially to the end of the course, so you can just turn it in whenever. So same is going to be true for homework 7, which I meant to post yesterday, but I'll post today. So it'll be due basically at the end of the course. It'll be very short. And then your exam when I post it, I can't remember if I made an announcement for the final exam info, but basically I will post what is going to be your final exam here in a few days. Maybe I'll post it on like next Wednesday or something, and you'll have until the 21st to do it. And then when you turn down on the 21st, and the reason for the 21st is because that's when our final exam was scheduled. So when you turn down on the 21st, you'll be done with the course. So I wanted to kind of keep the schedule the same as it would be if we were in person, where you'd be done with the course on the 21st. If we were doing all this in person. So anyway, all right. So I wanted to talk about non-Euclidean distance because this was kind of the aspect that was most intriguing, since we came to this upper half plane by extending our transformations from RP1, or from the real projective line, which we see as the boundary of the upper half plane. Extending that is how we got the upper half plane. And what is weird about the fact that we're going to have a non-Euclidean distance on the upper half plane is that the RP1 had no notion of distance. Right, because RP1 was something that arose from projective geometry, and in projective geometry there's no notion of distance. So this is really weird that we would get this. So how does this work? Recall that linear fractional transformations preserve the cross ratio. Right. In fact, this was kind of like the key quantity they preserved, right? So linear fractional transformations, they preserved the things you cared about in projective geometry, which was basically the straightness of lines, right? Collinearity. That's what was preserved by these fractional linear transformations. And so my question is, what do Möbius transformations preserve? Right. Okay. So question how do Möbius transformations so how do Möbius transformations maybe I should say alter the cross ratio? Okay. Okay. So we can check some of these things directly. So answer, well, on one hand, checking that the transformations that send x to x plus L and that send x to kx, these are the same. So these are the same as checking that the transformations that have been extended here that send complex number to complex number translated and complex number positively scaled. All right. So these two leave the cross ratio invariant, as did these. Of course, we know that the generating transformations for linear fractional transformations leave the cross ratio invariant. That's why the linear fractional transformations had the cross ratio as an invariant in the first place. So turns out that the cross ratio is also invariant under the transformation that sends z to minus 1 over z. Okay. You might complain for a second. You might say, wait, right, this is not the usual inversion generating transformation that we use. And you're right, but of course we can use the typical inversion transformation that we use because this combined with the transformation z to minus z bar is the same thing, right? So recall, maybe as an aside over here, I'll say note. Z goes to 1 over z bar is composed of z goes to minus 1 over z and z goes to minus z bar. Right, the usual reflection that we do. Okay. And so the cross ratio is invariant with respect to this transformation. Okay. So then the last thing we need to have generated everything here is this one. Okay. All right, this is the last thing we need. Unfortunately, the cross ratio is not invariant with respect to this transformation. So everything I've boxed here, so these are good. This one's good. This one is not. Okay. But not all hope is lost here because it doesn't do something random. It replaces the cross ratio with its complex conjugate. Okay, so this, however, z going to minus z bar replaces the cross ratio with its complex conjugate. Okay, and so, unfortunately, the cross ratio is not quite an invariant with respect to Möbius transformations. But it turns out this little thing, this little slight hiccup, doesn't actually matter. Because what we actually care about is not whether or not the cross ratio is like a total invariant of this thing, or of these Möbius transformations. What we care about is the cross ratio of 4 points on a non-Euclidean line, right? Okay, and in that case, we're in a lot better shape. Okay, so we'll see that. So, but what we actually care about is the cross ratio of 4 points on a non-Euclidean line. And in this case, that is, you have 4 points on a non-Euclidean line. It turns out that the cross ratio of 4 points is real. Well, what does that mean? How does that help? So remember, in general, when we're talking about this, we're considering the cross ratio of 4 complex numbers. So there's no reason to expect that algebraic combination would necessarily, be real or complex. It could be whatever, right? So it could be real, or it could be something that doesn't lie on the x-axis. But apparently, when you are dealing with 4 of these complex numbers that lie on a non-Euclidean line, what you get is that this cross ratio actually has to be real. Now, why is this? Let's state the fact here. So the cross ratio of 4 points on a non-Euclidean line is real. And thus, why do we care so much? It is equal to its own complex conjugate. And thus, is invariant under Möbius transformations. Okay. Now, the part that I'm actually proving is that the cross ratio of 4 points on a non-Euclidean line is real. These others, so one, there's nothing to prove here. If you have a real number, it's equal to its own complex conjugate. And by the previous comments that we said, since we had seen that the cross ratio was an invariant, it was invariant under Möbius transformations, except the single type of Möbius transformation that involved this reflection, sending z to minus z bar. And that particular transformation replaced the cross ratio with its complex conjugate. So Möbius transformations either fixed the cross ratio, either preserved the cross ratio or replaced it with its complex conjugate. And so, if you have a cross ratio that's real, it is necessarily invariant under Möbius transformations. Okay, so that is the important statement. All right, now, to prove this thing that I've underlined here. Okay, so proof of the underlined bit. Let Pi, Qi, Ri, and Si be points on the upper y-axis. All right, so maybe in my upper half plane, they look something like this. All right, here's Pi, here's Qi, here's Ri, and here's Si. Okay. All right. What's the cross ratio of these points? So by cancellation of the i's, the cross ratio is exactly what you think it would be. So it would be R, written in this order, it'd be R minus P times S minus Q over R minus Q, S minus P. Okay. All right. Now, it turns out this is the only thing we need. It follows for any generic non-Euclidean line right? So we just show this for the upper y-axis, but it actually follows for any generic non-Euclidean line by mapping the upper y-axis to that line. The important bit was what I said on the previous page, which I'll bring back here in a second. So it follows for any generic non-Euclidean line by, we'll call this non-Euclidean line L, by mapping the upper y-axis onto L by a Möbius transformation. Remember, while I couldn't say that in general the cross ratio on the upper half plane was invariant under Möbius transformations, it was invariant under almost all the generating transformations. The only one that changed it was the one that replaced complex number with minus its complex conjugate. Okay. And so, how am I done here? Okay, so let's go back, previous page. I can use these perfectly fine. And I can use this, right? So these, any Möbius transformation that results as a combination of these three generating transformations is good to go. All right, this is the only thing I'm not allowed to do. But to map the upper y-axis onto a generic non-Euclidean line, I actually only need to use these. I don't need this one. Okay. All right, and so to see how to do this, so there are two cases, right? So two cases. So first case, what could L be? L could be another vertical line, right? L is another vertical line, like the upper y-axis. So in that case, L is the line, x is equal to L. Well, then we map the y-axis to L via the transformation that sends complex conjugate, or sorry, that sends complex number z to z plus L. Okay. Because our points P, Q, R, and S on the upper y-axis were totally generic, right? They're completely arbitrary. Then this is going to be true for any 4 points that lie on this line L. Okay. All right. So that takes care of that case. And we know that the cross ratio is invariant under this transformation. Okay, the second case, L is a semicircle that has a center somewhere on the x-axis. Okay, so second case is L is a semicircle with center on the x-axis. Okay, so in this case, we first map the upper y-axis. We map the y-axis to x equals 1 by the transformation that translates by 1. Then to the semicircle with ends 0 and 1 by the map z goes to 1 over z bar. Okay. Okay. Now, what do I do? So now I can translate and dilate to get the rest, right? So lastly, I can dilate the semicircle to have the same radius as L. And translate its center to the same as L. Okay. All right. And so, since now we've actually combined every single one of these Möbius transformations to get this done, what does this mean? So we've taken care of both cases. We can map this upper y-axis to a generic line L. And so since what we said was true on the upper y-axis, that is that the cross ratio is real, it has to also be true in both of these cases. Thus, the cross ratio is real for 4 points on a non-Euclidean line. So this is the thing we're trying to show, but the reason why this was important is this allows us to say the next thing, which is that thus the cross ratio of any 4 points on a non-Euclidean line is preserved by Möbius transformations. Okay, this is the key thing. Okay. All right. So, our purpose, of course, in investigating this was basically because we were claiming that a non-Euclidean distance was something that was going to be apparent from working out all of this stuff. Now, quick question then. If I'm wanting to use this to discuss a distance, note that this is a function of 4 points, right? The cross ratio is a function of 4 points. The distance is a function of 2. Now, when I say the distance here, of course, I'm talking about a distance that I haven't quite defined yet. So what I'm really saying here is that something that we call a distance, right? When we talk about distance, and if you've talked about metric spaces at all, then you know the metric notion of a distance function. It's a function of 2 variables, right? So you're plugging in 2 points, right? A distance from A to B or X to Y or whatever. Not 4, right? And so how do you make sense of that? How can you interpret the cross ratio as a function of 2 points? Now, I didn't really state a question. Maybe I should say, how can we reconcile these? So how can we reconcile these? Well, the idea is that there's a key difference between these non-Euclidean lines and Euclidean lines. Okay. These non-Euclidean lines have a property that Euclidean line segments have, right? That they have endpoints, right? And so you can actually determine a non-Euclidean line by its endpoints, right? So a non-Euclidean line lies between 2 endpoints. So it lies between 2 endpoints. Okay. So example, really quick, is that the upper y-axis, what endpoints does it lie between? Well, here's the upper y-axis. Here's 0 as one endpoint. What's its other endpoint, right? So you might say, what is its other endpoint? If it's easy if it's a semicircle to see what the 2 endpoints are, but if it's a vertical line, how do you see what the endpoints are, right? So this is why it's important to, you might think the upper y-axis is too simple of an example, or too basic, but actually it's kind of the most important example, because if my line in question was a semicircle centered on the x-axis, then it's clear what the 2 endpoints are, right? So then the only thing that's unclear is when one of the endpoints isn't apparently on the x-axis. And so the other endpoint is at infinity. Okay, so the endpoints are 0 and infinity. Okay, now the reason we're comfortable using this infinity symbol and treating it as an honest-to-God point, of course, is because we have a perfect understanding of how linear fractional transformations and Möbius transformations respect this point we're calling infinity. Right? Infinity is the point that 0 gets sent to under the inversion map, right? X gets sent to 1 over X, right? Or Z is sent to 1 over Z. Okay, or even 1 over Z bar, right? So you might have a slight complaint here. So, warning, maybe. Note that the endpoints are not technically points on the line. Okay. So when you think of them as lying between two endpoints, they don't touch the endpoints, right? Which is kind of what's so weird, right? So when you look at the y-axis, here, this is the line from 0 to infinity. Now it never reaches 0, right? Because this maybe I should get a different colored pen here. It could be kind of hard to see. This x-axis is never actually reached, right? It's the boundary of the space. So it's not included, right? I drew it as a solid line here, but of course it's not included in the upper half plane. Right? The upper half plane only includes positive y values here. And so the way to view this is this line is continuing on forever towards 0, but it never touches it. And it's also continuing on forever towards infinity, but obviously it never touches it, right? Okay, so these aren't technically points on the line. All right, but here's why we're going to include them in the cross ratio anyway. But we include them in the cross ratio since Möbius transformations and the things that they were extended from, the linear fractional transformations, make perfect sense at 0 and infinity. Make sense at both 0 and infinity. Okay. So the Möbius transformations apply to all complex numbers. Also, 0 and infinity. Right, 0 is a complex number, right? It's got real and imaginary part 0. But Möbius transformations also apply to infinity, we understand. And so, if we take 0 and infinity as the third and fourth members So if we take 0 and infinity as the third and fourth members of the quadruple, on the y-axis that we dealt with before, which is P, I, Q, I, R, I, S, I. So we replace these with P, I, Q, I, Ri is going to be 0, and Si is going to be infinity, right? So we take this quadruple. Of course, we were allowed to make this completely arbitrary, but I'm going to replace R and S with 0 and infinity in this way. Let's see what this does to the Möbius transformation. Okay, so we saw that the Möbius transformation, let's see what this does to the cross ratio. That's what I meant to say. We saw that the cross ratio of these 4 points was real and that its value was R minus P S minus Q over R minus Q S minus P. Okay, but replacing R with 0 and S, so Ri with 0 and Si with infinity, what's something that we can do here? So what we can do is we can divide both top and bottom by S. You'll see why we're doing this in a second. So this is the same thing as R minus P times 1 minus Q over S divided by R minus Q and 1 minus P over S. Okay. But if S is infinity, this is 0, right? Dividing by infinity is 0 here. So this term is 0, this is 0. And then what I'm left with is 1. So this is R minus p times 1 over r minus q times 1, right? And that's because 1 over s is 0, right? Since s is infinity. Okay. But then this is equal to r minus p over r minus q. But remember, we replaced ri with 0, so r is 0 here. So this is minus p over minus q, since r is 0. And so this is just p over q. Okay. And so we began with a quantity involving all four of those points, p, q, r, s. Okay, but actually, if r and s are made the endpoints, then the cross ratio itself becomes a quantity that involves only two of them. It involves only the two of them that aren't the endpoints. And this is exactly how we're going to view the cross ratio, as a function of 2 points rather than 4 on these non-Euclidean lines. Okay, and so any Möbius transformation sends endpoints of a line, that's a non-Euclidean line, so any Möbius transformation sends endpoints of a line to endpoints so maybe I should say, for this specific example, not just any line, but the y-axis. So this is true, but for this particular example, all I care about is the y-axis. So any Möbius transformation of the y-axis sends endpoints to endpoints, but it is possible, in fact, it is guaranteed if there are certain Möbius transformations used, it's possible that 0 and infinity get exchanged. All right, I bet you can guess what Möbius transformation would exchange them. Okay. So, and if r is taken to be infinity and s is equal to 0, so we added in the opposite way the other time, then the cross ratio of pi, qi, ri, si is q over p instead of p over q. All right. What that means is that these quantities are not the thing that would be left invariant by these Möbius transformations. These aren't the quantities that would be unchanged. In fact, they would be changed. Okay, so thus p over q is not an invariant of Möbius transformations of the upper y-axis. This is not an invariant of Möbius transformations of the upper y-axis because it could get mapped to q over p, which is something different. But the absolute value of the natural log of p over q or q over p is y. Well, what's going to be the difference here between log q over p or log p over q? Well, because of log rules, the difference is going to be a minus sign. So we slap an absolute value sign on it, and we are good to go. Okay, right? Since log, oh, since log P over Q equals minus log Q over P. And so we have found a quantity that only involves 2 points that is an invariant of the Möbius transformations. Thus, we've found a quantity only involving 2 points that is an invariant of Möbius transformations. Well, again, following the Kleinian approach, you've got transformations. You've found an invariant. This is an invariant that involves 2 points. Okay? What might be the good thing that's a generalization of? Well, length or distance, right? So this allows us to make the following definition. So definition, and this is the definition of distance on the upper y-axis. Okay, so the non-Euclidean distance non-Euclidean distance that we'll call indist. So indist pi qi between points pi and qi on the y-axis is, so indist pi qi is the absolute value of the log of q over p, or p over q, doesn't matter. Okay. There's an equivalent formulation of this using integration. Okay, so you could equivalently define something that works out in the same way using integration to do it. Okay, you can think of it as scaling the usual distance computations done via integration with by a factor of whatever your variable is, t or x in the denominator, or t is better. Yeah, scaling by like a factor in the denominator. Okay. All right. So, how do we know that this is the correct notion of distance? All right, what would it mean to be the correct notion? Well, the idea here is that it should behave like distance normally behaves, right? So, and again, if you've seen metric space stuff, then you know that it should satisfy ideally it should satisfy the same properties that a distance function satisfies to make a space a metric space. And so one thing, you can already show that it's symmetric, right? Whether we're talking about the distance between P and Q or Q and P doesn't matter, just from the definition, right, algebraically. Of course, so one, this distance is invariant under all Möbius transformations. Since Möbius transformations are the geometric transformations, right? They are the analog of our Euclidean isometries for the type of geometry we want to do. Then it makes sense that that this quantity would be an invariant of the Möbius transformations. In fact, that this is something that's required for us by this Klein approach. The Klein approach, remember, says that the important quantities in the geometry I'm studying will be invariant under the transformations I've chosen. And so that's actually the definition of being an important geometric quantity, is that it is invariant under these transformations. Okay? The second thing is that it is actually nicer in some ways than Euclidean distance because it's additive. So what do I mean by that? If P, I, Q, I, and R, I all lie on the upper y-axis, okay, then the non-Euclidean distance from Pi to Ri is actually the same as the non-Euclidean distance from Pi to Qi plus the non-Euclidean distance from Qi to Ri. Right, so this is like equality in the triangle inequality. Right. Of course, you might say I'm cheating a little bit because we know all these lie on the same line. So, in Euclidean space, also, if you have three collinear points, then the distance is additive. Okay. But the fact that the distance is additive here, and we can check this really quick. All right. So, quick proof of this. What would my distance between P and R here be? So this would be the absolute value of log of R over P. Okay, but I can do some algebraic trickery here and write this as absolute value of log of Q over P times R over Q. Right, but using log rules, this is the same as absolute value of log of Q over P plus log of R over Q. Okay, and of course I'm looking at absolute value here. Normally absolute value has, there's an inequality I would slap here. So why can I say this is actually equal to the absolute value of log Q over P plus absolute value of log R over Q? Okay, well, you can think about that. Okay. All right. But this gives me exactly what I want, right? Okay. And so, what's a result of this? Here is where some weirdness creeps in. Consider the infinite collection of points. Two to the n I on the upper y-axis. Maybe let's draw a picture here. So let's draw a picture. So let's pick 2i. We'll say that 2i is here. Okay. So here's 2i. Next would be 4i. Okay. Next would be 8i. And next would be 16i, which I'm not going to draw. It's off the page here. Okay. in general, if I drew, this scaled out, so I zoom out a little bit, right, what would this look like? And you'd have points. And they would actually scale a little bit faster than that, but so these are your 2ni points. Okay. Now, what is the funny thing about this? Well, what if I considered, for instance, the distance between 8i and 4i and 4i and 2i? So what is the non-Euclidean distance between, let's do 2i and 4i? Right, what is that? Well, this is the absolute value of the log of 4 over 2. Right, this is the absolute value of log of 2. All right, so that's just log 2. What's the non-Euclidean distance of 8i, or sorry, I'll do it. It doesn't matter, of course, what order I do it in, but just to keep it consistent here, I'll say what's the non-Euclidean distance from 4i to 8i? So this is absolute value of log 8 over 4, which is absolute value of log 2. Right. So these are equally spaced. Right. And in fact, if I do this for any 2n, right, so what is the non-Euclidean distance between, say, 2 to the n minus 1 I and 2 to the n I? Right. So this is absolute value of log of 2 to the n over 2 to the n minus 1, which is absolute value of log of 2. So the 2 to the ni points are equally spaced. So this distance and this distance are the same. Right? This distance is log 2, but this distance is also log 2. So these two distances are the same. Okay. So similarly, like I said, if you plot out a bunch of these 2 to the n points, they are equally spaced, but they certainly don't look that way. Okay. And so what this tells us, for instance, is, as I mentioned before, distance and scale acts a little weird, right, when it comes to non-Euclidean stuff. So I'll show you one picture and then I'll be done for today. So here, these are faces drawn in the upper half plane, and these are all equal size, right? So with respect to this non-Euclidean distance, all these faces have the exact same size. So you see the distortion as you approach the boundary here. This tiny little microscopic face down here is the same size as this face up here away from the boundary. Okay. So this is an example of the weirdness that goes on here. All right. Okay. So that's all I wanted to say for today. As I said, so the last class will be tidying up some of the last things I wanted to say about non-Euclidean geometry. And then I will take some questions about the homework. I'll also hold some outside of class office hours for you guys next week sometime. So I'll let you know about that. I'll hold those. I might do it on the reading day. That way you're guaranteed to have time. So I'll do those office hours. And if you can't make it, I'll record them. So and that you can ask me any questions, any general questions you have about the class. The final exam, as I said, is going to be cumulative, but it's going to be a weird mix between problems like you saw from the homework and then some like more open problems. So anyway, I'll mention all that next time, and I'll put an announcement out today. Anyway, so I'll see you all on Monday.